Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So this is, I guess, a special episode that I did because I've just published a paper with Sid and Johannes. They'll give their full intros later, so I want to keep this a bit short, which is called Fluid Intelligence, a forward look on AI foundation models in CFD. It's a bit of a long title. I had to look exactly what we call the title now, so I didn't say it wrong. But it's something I'm quite proud of because it's been a real collaborative work to try and give a vision of how you could build a foundational model for CFD. And just to set the context, what that means, and the way I described it to some people, is like a ChatGPT for fluids. You know, that dream of a model that could predict any possible scenario of any plane, of any car, or of any data center, or of any pipe flow or anything. And not that our paper has the full answer to it, but we tried to look at the scaling laws, as in like what's the bottleneck to doing this from a compute, from a data point of view. It is still a scientific piece of work. It's a piece of research. It has hypotheses, but it's something we deeply thought about, researched, discussed with people in the field, you know, to get their feedback, and something that I think the three of us do stand behind as a coming of CFD, ML, applied math. And the paper's quite long. It's only 40 pages. And so the point of this episode was to have the three of us talk through it, really, so that hopefully if you're reading it, you understand it a bit more and you understand where we came from and some of the decisions we made, what we put in, what we didn't put in. And so, yeah, I hope you enjoy this. This does get into the weeds, but it's a topic that anyone who's listened to this podcast for a while has been a key theme, right? All the guests I've been asking has been about foundational models, has been about what can AI do for CFD? What can it do for things like Formula One, for cycling, for aircraft design, for space? So it's a culmination of some of that work, you know, of the past couple of years thinking in my head, and Johannes and Sid had similar sort of thought processes, and we all came together to write this paper. I'll put a link in the notes so you can get this paper on archive. It's a preprint, or if you just Google, I think like Fluid Intelligence, and if you put Neil Ashton, I mean, it'll bring it up, but you could put any of the other co-authors. So I hope you enjoy this paper. I hope you found it useful. It's been, fun piece of work, and I hope this helps to explain some of the logic behind it. So yeah, sit back and listen to this special episode. Thanks, Sid, Johannes, for joining. This is, I guess, a special episode because we put out a paper recently that I think has, resonated well with people. And we said, why don't we actually talk about it, talk about the journey, how we got to this point, some of the technical details, so that people, understand a little bit more than just reading the paper alone. But maybe before we begin, why don't we just set the background and for the two of you just to give a brief overview, you know, who you are, where you work, what you're doing, and your background, I guess, and then we can get into the paper. So, Sid, did you want to go first?
Yes, I can go first. I'm Sid Mishra. I'm a professor for computational applied mathematics at ETH Zurich in Switzerland. And I run the computational applied mathematics laboratory here. And what I do is my basic background is in physics and math. I did my undergraduate degrees in those subjects. Then I shifted more or less to applied and computational math. then after my PhD, a lot of the research was on numerical methods, numerical analysis, scientific computing, applied it to different areas, astrophysics, fluid dynamics, material science, different topics. And for the last 5-6 years, I've been working on using AI for solving physics problems, and with some success. First with physics-informed neural networks, and now for the last several years with neural operators, diffusion models, foundation models, and so on. So it's been a lot of fun.
Yeah, nice. Johannes?
I'm Johannes Brandstetter. I'm a professor at the JKU University in Linz, and I'm also a co-founder and chief scientist of MEI. I've been in the field of surrogates for engineering, if you want to call it like that, for approximately 3 years. I'm tinkering about how to build these surrogates that they really fit to industrial scale problems, industrial size problems. That is where I met you, Neil, I think approximately 2 years ago, and also where the paths of me and Sid were overlapping. And it's a tremendous pleasure for me to have a paper now with both of you, because it was very high up on the bucket list to have a paper with each of you. But to have it combined is like really a true honor for me.
Yeah, I think we met because you gave a thing at like an iClear workshop. I think I was organizing, but I remember where we really spoke was at a what was the restaurant? Was it pizza or Italian or something in Silicon Valley, where we met up, and that was where I think we first were like properly getting into this topic, and that was actually whilst I was still at AWS, and I think I was it like Christmas time or something, or January time? I can't remember what it was. So actually, when I look back, we'd sort of started having some of these discussions almost like a year ago on this. And maybe what I thought we could do is each of us maybe can set the scene in what prerequisite knowledge we brought, right? What before we really started to interact and I guess, blur these knowledges together, which is I think ultimately what the paper was. Maybe we can set the scene of like what our thoughts were before. So maybe if I can start it a little bit. I am not a machine learning specialist. That's the first thing. I'll put my hand up and admit I am not anywhere like the two of you who really are like super deep in the knowledge, but I was always intrigued on how far AI could go. And I sort of was thinking more from a very applied point of view. You start to build these surrogates, you have like 500 cases, it has a certain accuracy. I like all these ideas of scaling a little bit. So like if you take a solver, it works well for a simple problem, but will that same method work for a really big problem? And we know if we do like a DNS simulation, it works really well for a small problem, but the scaling means you can never really do it of a full aircraft, regardless of how good it is. And so with the AI, I was always like tempted of, well, is this just a matter of scale? If you just throw more stuff at it, is that the solution? Just more compute? Or is there something that ultimately stops it? And I guess the second bit was when I did go to iClear or NeurIPS, I was sort of amazed by the amazing talent, but at the same time, the sense that they were two different worlds, that you were speaking to these people who didn't have that practical sense of like using CFD for engineering, like actually designing something, but were looking more theoretical. And then you had the CFD side that were really good at that stuff, but just had no clue about all this amazing work that was going on. And I think that's why I'm always excited when I speak to people like you two who have much more of the sort of applied math, ML side, and you can educate me. And I feel like I'm absorbing of you. But how about you, Johannes? Where did you come into this? What was before we really started to go in this sort of three-way thing, what was your thoughts?
Yeah, approximately, I think, no, not approximately, pretty much exactly 3 years ago, ChatGPT came out. And at the very same time, I was at Microsoft Research. And there I pushed really, really hard for these foundation models. First, it was the Climax model, and then it was this Aurora model. And the gist of it was basically throwing as much data as possible into into the mix and trying to see what comes out, which worked very well. And which was a big motivation for me to go into this engineering. However, there's a lot of difficulties, differences. First of all, Aurora worked so well because it was all based on vision transformers, which everyone at that point understood how they work and how they scale and how to operate. And there is not a lot of control of the weather data because in the end, you download some weather data from different offices and different simulations, and they kind of all model the similar physics. So they have different discretization schemes, but they all try to have the same turbulence modeling schemes baked in. However, when you go to engineering, you encounter two problems on this axis. First, there is no scalable architecture available for doing a 200 million surface mesh, volume mesh Formula One car simulation. So you have to build the scalable architectures, and there is a big difference on the data regime because data can have so many aspects: how you discretize, what turbulence model you use, what meshing you use, what numerical scheme you use, and so on and so forth, which makes this very fragile and very hard to understand. And on both of these fronts, I tried to do my research and I tried to move forward, and that's where, from my side, the discussion started.
How about you, Sid? I mean, obviously, you've been working on this for a while, and there was like the Poseidon paper, and you've had these thoughts of foundational models, I guess.
Yeah, so I come from it from sort of similar viewpoint as Johannes. That's why we discuss and gel very well. So my perspective in the beginning was more, I'm a mathematician, so I wanted to essentially understand, if possible, rigorously prove how much of data is necessary for, and what is the model size that is necessary for an ML model or an AI model for that matter, to learn certain tasks, to excel at certain tasks, to generalize well. So this was, and I was not looking at vision and text like what most people look at, but I was looking at scientific data sets, physics, could be chemistry, and certainly engineering, because this is what I've worked on for a long time. And this was sort of the foundational question. And we already, some years ago, had some theoretical results which essentially said that, okay, things scale if you have enough data, but as Johannes just expressed, you never have enough data, right? I mean, this is the challenge in some sense, also the opportunity in this field. And then this is where foundation models took sense. The idea was that, okay, you have a large corpus of pre-trained data, and then maybe you can fine-tune it. And I have been working on this topic from different perspectives, just interested in the fact that can AI systems generalize to unseen circumstances, to unseen physics in particular, because that's my interest. And then, of course, I discussed a little bit Johannes approximately a year back. I think he was in Zurich, and then to his credit, he's the one who somehow brought the two of us together, because Neil, I know your work very well from the past, but I never had the opportunity to sort of meet you in person or interact with you before. So I think it is Johannes who sort of deserves the credit. Because, in a way, our knowledge base intersects pretty well. Means I know a little bit of CFD. You are the real CFD expert. Johannes is a real ML expert. I also know a little bit of ML. So we sort of, we complement each other very well. But I think the questions that sort of motivate us, drive us, are very similar, I would say, to some extent.
So I thought maybe it would be useful for people listening. So this paper, Fluid Intelligence, Forward Look on AI Foundation Models in CFD, which, by the way, I think it took us a while to figure out what title we should have. Quite a few different titles. Maybe what we should do is kind of go through it section by section. Obviously, we're not going to be able to go in full depth, but just describing maybe why, we had some of the things. And hopefully then by the end of it, people will get more like how we came to this conclusion. I think it's fair to say, isn't it, that the way the papers turned out was not exactly how we went into it. It wasn't really the idea to do it this way. But I think it sort of organically, we kept having meetings and then we would be like, yes, for sure, this is how, yes, we've done it. Okay. And then you're like, actually, the data's showing something different. And so it definitely has been a bit of a journey, which is what all good research should be, right? It was sort of live research over WhatsApp, essentially. But yeah, maybe just, I guess the first section, the whole CFD process, I think was borne out a little bit, or at least partially, when, Johannes and I were talking originally. And I think there was this little bit of, and I don't want to put words in your mouth, Johannes, but I guess you don't come from a traditional CFD background. So some of the stuff, you kind of knew, but you wasn't as obvious, like the industrial side to it. And I think that's when we realized that it might be useful for people to have almost that little bit of a go-to reference that highlighted this idea that it isn't just a single PDE that you just somehow need to model. And so it is difficult, and probably some people who are reading this and they look at the geometry, the physics modeling, the meshing, people I'm sure will find holes or will find bits that couldn't be covered. You would sort of need to write a textbook, and people have wrote textbooks, right, on this. But I think what we were trying to get across is just how broad the input space is. And I think that's where you, Johannes, and Sid like this sort of distributional way of looking at this, like trying to look at it in a way that would set it up to have some link to the LLMs, right? That was the way you wanted it, was it right, Johannes?
Yeah, fully 100%. I think that for machine learning people, the most important equation of the first half of the paper is equation 9. So what equation 9 is, we are basically saying you can deconstruct the CFD process into an input vector which has the turbulence model, the geometry, the meshing, and all these parts in it. And this input vector you can use to have a look at the input-output relations, which makes it very clear that if you want to have a foundation model, it surely needs to capture all these variations in the input vector. It also makes it clear that if you fix a few of these conditions, for example, if you use same inflow condition or same boundary condition, that the space of variations gets just much smaller. And the first section, which was mostly written by Neil, is actually really thought to explain for machine learning people how to come to this input vector, which makes a lot of sense, because suddenly you don't think of complex CFD simulation anymore. You think of input-output relations, and that makes it also easier to compare existing data sets and to understand which data sets can be actually mixed, and where mixing results in two very disjoint distributions. From the distributional point of view is Sid's way of thinking, which I got from him.
Yeah, so maybe just to add to the mix, actually engineers like this thinking, right? A systemic thinking. So you can imagine that there is a system, and to a certain system we feed some inputs, and we have some outputs at the end of the system's work, right? So if you think of machine learning or learning in particular, it's sort of task specific in that sense that a learning system has an input or a set of inputs, input vectors, and a set of outputs, the output vector, output functions, fields, whatever you call it. And equation 9 is sort of providing that, right? Where the distributional perspective comes in is that you cannot sort of have everything under the sun, right? Means you have to sample from a distribution. You can make this distribution as broad as possible, but once you sample from an input distribution, then in some sense your output distribution is highly conditioned on it, right? Because you might add some noise at the time of measurement of your system. So it's a very natural sort of mathematical perhaps or algorithmic thinking about machine learning, that you think of sampling from a distribution, take the samples, feed the inputs into the system, observe its output, and then all the AI system does is try to learn how the system sort of propagates or evolves. And this was sort of the thinking that I always keep, and I also teach it to my students in class, that think of everything in terms of systems. What's your input? What's your output? What's your input distribution? What's your output distribution? And then there's a lot of clarity. Because without this clarity, then we don't know what we are talking about, right? It becomes vague. And this is what I want, that mathematical precision. And this is, I think, useful to have so that we know what our target is.
And probably, maybe I'll use this point to jump forward a little bit, just because it seems an opportune time around the Appendix B and the whole notion, because as soon as, and just to say, Appendix B is this idea of some flops per cell per step. And I felt that was important because one of the objectives coming into this was to some way quantify the, if you're generating a data set or you're trying to calculate the costs, how do you do it? And it is obviously massively dependent on those CFD inputs, that equation 9. But one of the things that it is as well is the code itself. And this is I still don't think we have it perfect, but it was an attempt to say, right, if you are running a RANDS solver, you are going to pick certain inputs to match that. Like they're never done in isolation. If you pick a RAND, you're probably going to pick an unstructured grid because you're probably going to be doing complex geometries that you need to run fast. And because it's a steady state, you're probably going to go implicit. And because it's unstructured, so there's these sort of secret, yes, you could technically pick a different combination, but then they're more extreme. So the idea was to say, well, if you do that, you're more likely to do that. So let's clump that as one category, which was how we had that sort of implicit RANDs unstructured. It's sort of, if you look at many of the ISV codes out today, they have sort of centered around that choice. But then if you're going to be doing like a 500 million cell LES, whilst you could do it with an implicit unstructured code, it's not the optimum way of doing it. And it would have massively misrepresented it. So we thought, well, let's pick, and there are examples of companies out there who do have, an explicit, because now you are trying to time resolve. So using implicit doesn't make as much sense. You're probably going to do Cartesian because in this we picked warm modeled LES, so you don't need to resolve the boundary layer. So it's fine to use Cartesian. And it's a GPU solver. So we and again, they're categorical choice in a way. They're picking which inputs and clumping them. And so there's a million other combinations. But the idea was to say, and maybe we'll get onto that in a minute, a time step and a cell is not equivalent because in the explicit, you're doing hundreds of thousands of time steps. And yet in the steady state, you may be just doing hundreds or low thousands. But that flops per step per cell, which is like how much it costs to do it, is the important, multiplier in this. And it's one that I think there's lots of holes in it and you could calculate it in different ways, but I still think it at least gives you a picture. And I'm hoping that people listening to it, I'd love to see people test that theory, like how close are we to it? And it'd be good to get feedback, if there's certain things people disagree with or which is, I guess, part of the point of putting a preprint out, isn't it? It's to say, here's something, give us feedback. But we got to that bit CFD, and I was pushing for this more and saying, I still think we need to explain AI. To the AI people reading this, they're like, I know that. So that fundamentals bit, how did you sort of think about framing the whole? I think the maybe the sentence that depicts it the most is CFD is not a language. I can't remember which one of you wrote that, but I thought that was quite good.
Yeah, I did, but
maybe let me add before we jump to that. Let me add one thing for the ML community. So important to understand, and this also when I started to realize this, I don't know, 1-2 years ago. In engineering and in CFD, it's not that you make choices on fidelity and that basically results in everything what Neil just said. It also problem specific. So if you try to simulate a plane which is in cruise condition, certain CFD choices are okay. So you don't need higher resolution or a better turbulence model because certain turbulence model are capturing what you actually want to have captured, and then you can do all the results in your parameter vector is so to say limited. So it really depends on the problem. It's very different than what we usually know from machine learning, that you have my high quality data and my low quality data. There is quality always comes with the problem setup. And this is very important to convey to the machine learning community, that it really depends on the problem, what you're using. And that is, that's already the going to the ML part of things. I think it was a quite eye opener discussing these LLMs. So what token means for LLMs? I mean, in LLM, everything is so straightforward in a way. You have your documents, and your documents you have your tokens. You have a bunch of documents. You have many tokens. This is how you construct your learning tasks. And then we tried to map that to CFD, which was much harder because you have these data sets where you have suddenly these huge geometries with 500 million meshes or whatever. So is this like one data point? Is this should you count the tokens, but then the additionally you can subsample many different input combinations from this data point. So how is this all coming together? And at that point we were really saying, okay, let's really write down what people do in language and then make the connection why CFD is not language. And this is, I think, where Sid should comment.
Yeah, so why is CFD not language? Well, for starters, I think there are so many obvious differences, right? So in language modeling, you have this entire notion of tokenization, which is a very sort of clear paradigm, right? So what you have is you have these words or pieces of words, and then you convert them into vectors through the process of tokenization. And in fact, you convert them into entries of a code book through what is called quantized tokenization. So your tokens are essentially living in some very large code book, and they are sort of entries or on that register, right? And then all that you do in language model is, given a distribution on tokens, you sort of sample from the conditional distribution of the next token, right? So it's very sort of mathematically clear cut in some sense. In a way, it's very non-mathematical because language, but thanks to tokenization, we have been able to push that into a very sort of clear cut learning objective. This is different in CFD or in physics in general, right? Because for us, the learning task, everything is in equation 9 in some sense. That is our master equation. And what does it say? That when you sample, let's say that we fix the categorical variables. This is always the case. You have runs or LES or the structured, unstructured, these sort of categorical choices. Once you fix the categorical choice, then you condition that distribution, that input distribution upon this category. And then when you sample from this, you are essentially sampling functions, the shape, for instance, right, of your object, or the flow conditions, which could be vectors or even single parameters, boundary conditions, and so on and so forth. And your output could be a solution field, could be a sort of quantity of interest, drag, lift, and so on. So the learning objective is very different, just looking at equation number 9. So we cannot... maybe someday we'll be able to quantize everything so that everything is just written in terms of distributions of tokens, and we can do some next token prediction. But this is unclear to me, at least, and I have worked quite a bit on this, whether we have the accuracy, because, it's not enough that the word is close enough to what, because as humans, we have a lot of slack in how we understand, right? But if the drag is 20% off, we are finished. So we have to be accurate. So to me, I think it's very important to remember that the sort of input-output setting, the learning task, is very different, and that leads to a very different kind of formulation, which is what there are many similarities, right? Means after all, means there are more similarities and differences, but the differences here are very, very important. And I think the biggest difference is that our distributions, our inputs, our outputs are very different. And just to keep that spirit is, because as Johannes argued, means what does it mean? See, if you take a huge corpus in language, you have a lot of tokens. But if you look at a flow field, a lot of it is going to be void, right? So it's not very useful information. So you need that sort of global coupling, which is probably different from language. Maybe one day, when we have very good tokenization for physics, this might change. But at the moment, we are not yet there. I don't know if you ever get there, but we are not yet there.
And then I guess the next section was, again, it's impossible for us to do a complete job of it because there are papers dedicated to just this. But really that review of, and we should say, I mean, we had a much longer version of this at one point, but then we put it down, which was the different use cases of AI. And I think we were conscious that we are focusing on the, I guess, surrogate use case, but it is fair to say that there are other use cases of AI for CFD around like, post-processing vision stuff, trying to automatically find patterns or initializing solutions. Or I think the most famous one in the CFD world that I'm not sure if both of you have tracked much, but in some ways I felt hurt AI, which was the turbulence modeling. I think there was this idea that, and I think like Chris Rumsey and Sparlards and people from NASA had some of these turbulence modeling workshops, and Karthik Doraisamy was one of the first for this. I think Turbulence Modeling in the Age of Big Data, or I think it was that title, something like that. And really great piece of work. And it sort of made sense that a turbulence model, being so empirical in some ways, hand-tuned to coefficients, that ML could do a better job. And, for years people tried it. And I think even today, it never really generalized. And when I speak to people who are maybe not deep ML people, that sits in their mind as like almost the AI thought that it could build the ultimate turbulence model. And so I think that's why, at least personally, and I think you both agree, we steered it towards the surrogate modeling side because it felt like a well-defined problem that has got probably the most to gain. Like the idea, like we say, if you build a surrogate, the inference is in seconds or less than a second. Nowadays, it can give you full volume, full surface prediction. And making an improved turbulence model is great, but you're still going to be bound by the same time constraints that a CFD simulation gives you. So I think it's just, we want to make that clear. This is not of all AI for CFD. This is in some way a subset of the surrogate modeling, which is, I guess, the foundation model question.
Would I say something? Because since you raised it, maybe I get this off my chest. I've always wondered, or often wondered, why don't turbulence closure models with AI work so well? And there is probably an obvious reason for that. And let me sort of state what I believe could be a reason, right? So the reason is that this mapping that takes data to a turbulence closure model is a very, very badly behaved operator. If it are a map, very, very badly behaved map, there are many choices that you can, many knobs that you can tune in the turbulence model that can give you the same flow outcome, right? So I think it's an extremely ill-behaved operator. And in a sense, it is not making use of, because eventually people are learning like 3-4 parameters, right? Or 5-6 parameters in these models. And machine learning is about big things. If you use neural networks to learn a one-dimensional function, it will always do very poorly compared to its competition, right? You can just take a polynomial and get a better fit. So machine learning only works in a very large dimensions, large scale. And this is why I think the bad behavior of the underlying map and the fact that you're trying to solve a low or an artificially low dimension. I think the problem is really high dimensional, but you're trying to solve it in this low dimensional setting meant that the chances of it generalizing beyond this specific flow regime are very, very low. So perhaps that's one of the reasons. Whereas in a surrogate model, on the other hand, it's a really high dimensional problem. Your input vector could be millions of dimensions. Your output vector could be 1 billion dimensions, Neil, right? In your driver ML data set, for instance, if you learn the volume field, this is over 1 billion points. So in principle, and this is where I think AI or ML models can excel compared to turbulence modeling. So our choice was perhaps based more on pragmatism, but I think there is a deeper underlying reason behind that.
Yeah. Jans?
And there's two more things which we did not consider. So we were always in all our learning tasks, we were always in the large data limit. So basically the model shouldn't learn any spurious correlation, but it should really generalize because it has enough data, which is usually in this surrogate tasks where you have 100 samples, 50 samples, and then you should learn to generalize across geometry. That's quite hard from a machine learning point of view. So it's really in the large data limit. It is fully transformer based in a sense that we train with a simple MSE loss and no physics information is added, or just really standard training. and it's in distribution, so no out of distribution questions are asked. This is the setup, and in this setup one can formalize things. Otherwise, it gets very, very tricky. And we got a lot of questions in how do you think out of distribution works and so on and so forth. I think this is beyond the scope, and this is also where experiments are needed.
Yeah. So, and I think, again, the point of the paper was really, this is on every meeting I have with every commercial company or research company is just trying to get a sense of is a foundational model possible? And that's where you start to get into the numbers game. And that's where things did seem quite ill-defined. People may read this and say, oh, yeah, that's obvious, or I knew that. But I don't think it was even obvious to us before. And we kept sort of changing things around. We weren't fully aware of until you put pen to paper and start to do some of the maths, it's not obvious. And I think, I think it's fair to say that, Sid, this was the bit where I really learned from you, and I think is the strength of the paper, is that Johannes and I, when we were talking on the side, we were like, we wanted Sid to bring some of the maths, to actually bring some of the rigor, because you can do, some back of the envelope calculations, but you need to try to formalize it more. So how did you go, if we go into like the section on the actual scaling laws, so section 5. So what was your sort of thought process? How did you come up with these scaling laws?
Okay, this is a very, very good question. Actually, this is a disclaimer. We know this, but I think our listeners and viewers should also know this, that till the night before the final submission, we were still working out the final numbers and so on. So it was a very iterative process. Nothing was set in stone. And I was surprised. And the whole point of research is to be surprised, right? No, as I said, I have worked on a mathematical formulation of some of these questions in different sort of domains before. So for me to understand, we should also say that these are hypotheses, right? We don't have end-to-end proofs. We have not yet built such a foundation model, but we believe that these are very reasonable hypotheses because they hold for small scale models, they hold for language models perhaps, and so on. So the basic formulation we had very quickly, if you remember the sort of the first equations, how it scales with model size and how it scales with data size, this hypothesis we had pretty quickly. I think what was fun was to sort of try out different implications of these ideas, of these exponents and so on. The fact that you get power laws has been known for a while. You can show something with statistical learning theory, but in the LLMs you have the Kaplan et al., the famous scaling paper. You have the Chinchilla scaling laws. So there is quite a bit of work also in the domain that we work on. Is much less, this is surprising. Johannes and I are among the very few people who even discuss this question. If you look at some of the foundational texts for scientific machine learning, this question of scaling is not even there. If you look at some of the original papers, there's no scaling. You have a table where you have, at certain resolution or at a certain scale of data, these are our errors, and we compare with 10 different models without any understanding that if you change the data or you change the model size, the picture can be very, very different. So I have been sort of investigating this both theoretically and empirically, but to do it at this scale with a proper foundation model, to sort of have different scenarios, right? In the paper we have a low fidelity, probably not the best way to express it. But I think the key was to be able to formulate everything in terms of a common quantity. So in the beginning, we were looking at the model error. If you remember, we had an epsilon, which is the model error. We formulated all the complexity estimates in terms of the model error so that the theory can give us some predictions. But at the last moment, I shifted it to the number of samples so that everyone understands, no one understands what's model error, but everyone understands how much of data that you have, so that you have a common dictionary to compare different things. And we had these three scenarios. We had this, let's say, RANS, steady state RANS. We have an LES, but we only look at the time average. And finally, we did this full transient LES, and we compared the three, and we came up with, I would say, some surprising conclusions. Perhaps we are going to talk more about it. But what really surprised me, later on it was obvious, but in the beginning what was not obvious is I maintained that data generation was going to be the dominant cost, right? I think all three of us believed that, and we wanted our theory to show that, and our numbers to show that. But it's only by this iterative process of discussing that we realized that, okay, in the small data regime and small model regime, you have this actually holds true, but there is this crossover point, there is this critical limit, and that's why the paper is really, really interesting. Perhaps we should talk more about that.
Maybe let me add here one thing, because Sid, you mentioned that people don't look at scaling laws, so they try everything at low scale or with one resolution. And then there's actually the other extreme where people say, okay, we just burn millions and millions of dollars and we get lots of different data, we bunch them together, and what we get out is a model which solves it all. And that was my entry point into this whole area. That's why I pushed so hard to write everything as a composite vector, because that makes it very clear that it just doesn't work if you throw data together. And therefore we had set up this RANS versus LES type of things, because we all agreed that you probably cannot mix RANS and LES simulations so easily, and that the choice you make on this has a tremendous impact in the data generation and in everything you do, and all comes down to a modeling error you take into account. You basically, so but before doing that, you already take a modeling error into account, which has the consequence of all your future steps and all your scaling laws and everything you obtain. And this is something which is not clear to the machine learning community, which is very, very different than how machine learning people think. So that's why we have these three different setups of these modeling paradigms.
Yeah, and I mean, we can come to that a bit later as well, some of the open questions, and I think definitely the mixing of fidelities was something we kept going back and forth on, but maybe we should leave that a little bit towards the end, because I think that's definitely the open question. One thing that I did want to highlight is that transient one, and maybe to explain a little bit more, because, and again, it's true what Sid and you said as well, Johannes, about our assumption going in. I think I've even said it on this podcast in a few opinion things where I said it felt to me that data generation was the biggest bottleneck, and the idea that you could use transient data felt like intractable. But I changed my tune a little bit when I'm speaking to the two of you, because I think, one, we started to realize that you run a RAND simulation and you, in some ways, use all the information that the simulation gives you, because you can't take an early mid-simulation checkpoint because it doesn't have any physical sense. The solution is converging to a steady state. With the transient, on the other hand, we spend 5 times more, 10 times more, depending on the solver, to generate this data. But we only use the time average checkpoint. All this data we're sticking out, we don't use. And some of the early papers, I guess, on like mesh graph nets, had this idea that you would train on the time steps, because it was like a cylinder flow or something. And that was always intractable, because you said, I can't store all that data, I can't use all that data. And so I think it's, to be fair, today, all the state of the art work in an industrial way has always just been a steady state or some time averaged. And I thought, okay, you'd need petabytes of storage, unbelievable amount. But I think one of the findings, but there's a nuance, is the idea that if we do run a transient simulation, can we take, let's say, a 50th or some of the intermediate data, which can be extra samples. And I think that was something you both mentioned, but Sid in particular, I remember you mentioned that from some of your earlier work. And that does seem to be a key finding, right? That if you can we're not sure how much you could use, but more than one, right?
Well, I can talk about it a little bit. Again, I think a distributional perspective gives you some insight here, right? Because what we're learning when we are learning a time-dependent process is that we are learning the evolution of the time-dependent operator, how things vary in time. And in principle, we are learning, given a snapshot of the current state, what would be a future state given the lead time. This can be done directly. This can be done autoregressively. That's a detail, right? But essentially, what you do is that you sample the data distribution in different ways. Of course, if you just have very, very tiny time steps, if you learn every single time step, this is useless because essentially you're learning the identity then, right? But if you learn large time steps, which is what surrogates allow you to do, you're really sampling the distribution at different ways. And I think that makes a lot of intuitive sense. In my previous work, we had demonstrated, I think others have also demonstrated, that you just imagine that you're learning the steady state from some inputs and just using this training where you learn the transient information too adds value. You can reduce the number of samples, you can increase the accuracy and so on. I think Johannes likes the perspective of data augmentation. This is one valid way to think about it. I would just think that you are just getting more data from sampling more data from the underlying distribution. And because of that, then you have this behavior. Of course, what happens is you lose information if you sample too much. And but if you sample too little, downsample too much. If you downsample too little, then it's too much in terms of training and storage and so on. So the golden mean, which we don't know, it could be problem dependent, is to sample a few of the things, 50th or whatever we said 50th, based on some ballpark, and then you do have some gain. And this is not 50 times better, but it's perhaps square root of 50, which is 7 times better, right? This is what we put the number 5, which is based on some previous work. But I think it makes a lot of sense intuitively as well as mathematically. And I think it's a very important, one shouldn't throw away the transient information. I'm pretty confident that it will help you.
For me, it was very eye-opening because we always had this discussion. In LLM, you basically you assume you see each token once. So every token is seen once. And what does this mean in CFD? That means every data point should be seen once if you go for large-scale limits. But well, if you have 20,000 simulations, which is already a pretty big data set, that's kind of not possible. But then this traversing in time, what Sid mentioned, that you need this time dimension, is actually also what happens in space, right? So just subsampling one data point is not giving you the whole information. So therefore, you can see the data points multiple times, and that's the same of traversing in space. In time is the traversing in space, and that still corresponds to this LLM paradigm in the infinite data. So this was quite enlightening for me when I understood this by the explanation of Sid over the temporal domain.
I think the other one that maybe is a key thing is which comes later when we show the numbers, is the downsampling, and I think this matters from the training, but also the storage side. That, when I was generating the driver ML or Ahmed or whatever data sets, we provided the full data, the full volume, the full surface. And that was partially because even at the time we were just unsure of, it felt like we were downsampling just because of memory limits. And that was probably more because of the graph neural net approaches that we were trying at the time. But it seems like and I think you have it, Johannes, in a couple of your recent papers where there's a saturation point of how many tokens in this case do you need, where if you go beyond it or lower, if you go beyond it, you don't gain anything. And so I think, what was that? I can't remember the number now. What was it on a 100 million cell case with 3 million surface? You're only needing hundreds of thousands of tokens rather than the tokens equals the number of cells. And that is a massive difference, right? It fundamentally alters the cost of training versus if you had to take everyone. How much of that how important do you think that is, that downsampling, essentially?
I see it again more from the perspective of a person who does not come from a CFD PhD. CFD needs this fine resolution because otherwise simulations just don't converge. We artificially have this fine mesh because we have to enforce physics onto the computer, and we as humans cannot do that with a mesh which a machine learning model would understand. So we need this fine resolution for the CFD to converge. I mean, this is a bit bluntly put, but in a way. So the machine learning model does not need this fine resolution to understand the problem. And in fact, a machine learning model is not solving the CFD. It's not about convergence. It's not about implicit time stepping or whatnot. It's just about getting the information. And information is not the same as a CFD convergence criteria. I have not understood this at the first, but I think it boils down to this, that you can have the full information in a downsampled case. And therefore, I would assume that if you do a RANS versus an LES simulation, it would need approximately the same number of tokens. However, you're modeling different physics. And for the CFD, you need much finer resolution for the LES. So this is a very big difference between simulation and machine learning.
Sid, is that how you see it as well?
Yeah, more or less. But from a purely mathematical perspective, I just formalize a little bit of what Johannes exactly said, right? So the reason why we have extreme grids in space as well as very tiny time steps with explicit methods is because of accuracy and stability requirements. That's why we need extreme grids, so that we can resolve small vortices, we can resolve, and in time you have the CFL conditions. So if you have a very small spacing in space, mesh size in space, you have consequently a small time step. Now, once you have generated the simulation, and I urge everyone to do this experiment, they can themselves downsample. And then they can downsample, they can put it aside, and then they can upsample using some simple interpolant, right? Means you don't even need a fancy interpolant. And you'll see that the errors that you make in this process are tiny compared to your modeling error. Your modeling error is, of course, if you just downsample at 10 points when you have 10 million points, you make a huge error. But as long as it is reasonable, and that's what we sort of argued in our exact numbers, I think we said that we downsample to like 8 million and then we do something more. And so we had some concrete numbers. The interpolation errors are so tiny that no information is lost. And this is the big difference, because in a CFD setting, if you sort of simulate it at that resolution, you get nothing, right? But once you have simulated, you can always downsample, both in space as well as in time.
Sid, you should probably explain what you tell your PhD students, what they should do with a data set, because this is something I found very interesting and which I learned from you.
Not just my PhD students, my students in my class. I always say when you get a sort of scientific data set, what you should really do is to first see what is the essential spatial scale that you need and what is the essential time scale that you need, right? And the best way you can do this is that you take your data, you keep on downsampling it till you can arrive at 1% error. 1% is a number that I've plucked out here. It could be 0.5 or 0.2% error. And that is the information. You don't need more than that, right? That's an extremist. It's the same with time. You don't need every single time step. How much can you downsample? And then you have an idea of the spatial and temporal scales of your problem. I also tell them to look at the sort of variation of the data. So compute things like mean and the variance. Say what is sort of the noise to signal ratio, what is standard deviation over mean, so that they understand what the data has. And it is very useful, but as always, students don't always do it, right?
Yeah.
They want to take the data and they want to run a model, and and yeah.
So if we go, into maybe the numbers a little bit,
we should.
And I think and it's true what Sid said, and it's true, things were changing, but it was almost a good thing that we were doing that, because we were trying. There's always a temptation of like groupthink, where you all sort of don't want to challenge each other. You've sort of got to a conclusion and nobody wants to challenge it. Where I think we were all open to challenging each other's perceptions. And I know as you described, definitely came into this thinking the data set was the biggest. And that seemed to be true in the early numbers we had. But then, so if we go through, so we have this low fidelity, high fidelity transient, but maybe the more interesting one is the table 4, which is this large, extra large, extra, extra large, and then the graphs in figure 3. And what we were basically trying to show, so maybe for the data generation, I can go over some of the numbers, and maybe Sid and Johannes can talk a little bit on the model training. They are by definition. We did try to give some estimate based on the sort of error floor, I guess, but it is still tricky to estimate the number of samples. And that's why we did try a couple of approaches. One was, I guess, the more statistical, more mathematical way of doing it. And then the second way, which is Appendix 3, was, I guess, the way that I think more CFD people have looked at it, which is just simply this sense of, well, how can my model predict a plane if it's only trained on cars? You know, it doesn't matter how many cars you give it, it's never going to be able to predict a plane, right? I mean, that's just common sense. And one of the challenging features of CFD, and it's an interesting intellectual exercise, is CFD is very broad, very broad. The possible geometries and flows and physics that you can do with CFD is quite extreme. And so if you look at like Appendix C, I'm sure I missed out some, but it is amazing when you start to go through and you think, okay, it's cars, right? But then it's also lorries and trains and planes and space planes and rockets and engines, data centers, buildings, combustion. And then what is really interesting is some of that chemical side. Yeah. There's a huge industry all doing these like multi-phase flows, multi-physics, cement mixing, ice cream making. There's just so many. And each of those, the input, that we described, which is essentially boundary conditions, initial conditions, physics modeling, we purposely summarized it in the sort of turbulence model, because turbulence model is one of the biggest impacts. But once you get into these chemical and process, the additional source terms you need to model some of the physical processes does get it big. So, with those numbers, you can easily reach into the millions of samples. Now, what I think is not entirely clear to me is just how much cross-learning there is between, there is obviously you could argue a low-speed plane shares quite a lot with a car in some ways, but an ice cream is quite different. So there's obviously some, learning. But anyway, that's how we got into the millions. So we said 200,000, a million, and 2 million. We purposely gave the Python code to this, so you could change these numbers yourself, because they will change. If you went to now 20 million, it would change the numbers. We went for the 500 million cells. This is based on some work that I've been doing for an upcoming data set, which was on an aircraft. And the 500 million is sort of at the... It's a number that encompasses quite a lot of cases in terms of, the Reynolds numbers, the sort of structures you get. 500 million is quite a good number to represent anything in the, let's say, LES of buildings, of planes, of cars, or you could obviously change the number, but it is representative of that sort of case. Steps is tricky because it depends on the mesh size, the total convective time you'd want to go for. But we had to pick some numbers to base it in. So that was the 200,000. The flops per cell per step is quite aggressive. If you do the maths on your own code, if anyone's listening to this, you'll probably find that represents the ultimate today of efficiency of a code. You'll probably find if you run, I don't know, OpenFOAM, you'll definitely not be at that flops per cell per step. It'll be quite a bit higher. But if you go through the maths, it's not unreasonable, but it is quite aggressive. So I state that because the number of hours you may need would be more if your code wasn't that well optimized. Then in terms of, just to finish off some of the logic of this, how we got to the hours. Now, this is tricky and does get into a bit of the HPC side, but we essentially took the flops and then worked out if you were using FP32, which is reasonable for like modern day CFD. There are some cases that would need FP64, but quite a lot use FP32. So we took the flops that was available on the system, but we realized that because many of these codes are memory bandwidth bound, the actual flops they can use on the system is still relatively low. So let's say 15%. And that's ultimately then, once you take a cost, and I took these costs, if you go across all the different cloud vendors, all the cloud computing vendors give their costs publicly. So I think $8 was like probably the best price with a reserved instant. If you sign up and you buy them up front for 3 years. But my logic was, if you're spending $100 million, you're probably going to do that sort of deal. You're not just going to pay like an off-the-shelf price. You are going to commit. And then the storage was the same. It was like one of the cheapest cloud pricing for storage. And so that's how you got to these 10, 50, 100 million. And just to finish off on the data generation side, what we did do is we put into figure 3 in, I think, the sub-figures around the D, E, and F, that if you did change the amount of flops or the size of the mesh or the cell size, how that would change. And so those numbers could go to 200 million to 500 million, but they sort of set a ballpark of where we're at. So then for the model training, I mean, one of the things that we were working on till the last moment was like the flops question, right? That was a tricky one.
Yeah, you want me to take it? But before that, maybe this is, some people have commented on this to me privately, is that our assumption is that some of the practitioners, they claim that our numbers are too aggressive because most of the codes at the moment, or many of the codes, don't have the sort of GPU capacity yet, right? And if you're doing this on a CPU, then this numbers change dramatically, or they will change, right? So perhaps maybe Neil, you are the expert on this.
Mm-hmm.
What's your thinking about this? We have made a big assumption, a big bet here that everything can be generated on a GPU at FP32 with a very aggressive flops per cell, which we don't vary much in figure 3. So what happens if you are stuck with a CPU code?
Well, yeah, interesting question. And, obviously I have to, as you do in papers, put like, what's your conflicting thing? I work for NVIDIA, a GPU company, right? Obviously. But, people hopefully will know that I'm not this is not a marketing or sales exercise. I think it's pretty defensible to say that if you look across all of the supercomputing centers, all of the people developing codes, any new code, if you're going to start a code from today, are you going to write it on the CPU? No. I mean, that's just the case. But you are absolutely right, which is sort of the comment on OpenFOAM. If you were to run with like a CPU code, I'm pretty sure those numbers would be 10 times higher.
Exactly.
Which would basically make it, you couldn't do it. That's sort of my logic, which is a little bit why the it is irrelevant for the GPU topic here. Yeah, but you're right. Probably in the revised version, we probably should give a bit of a caveat of, I just take it as an obvious thing, but maybe I'm a bit like surrounded by this data. For me, it's a no-brainer that you do it. But we could definitely add, but it would make the numbers quite scary.
Absolutely. And this is the point that I wanted to make. But maybe I can walk, and Johannes can just add, I can walk us through the choices we made regarding the model training and what are the different things that come in. So before that, regarding the number of samples, so it does turn out that it was a fortuitous coincidence that this 2 million is roughly 2.5 million is what Neil arrived at by just sampling this entire data set of, chemical reactors and rockets and cars and everything in between, right? But independently, because we have some clue about what is this. So there are two key numbers of exponents here. Beta in table 4, if someone has to look at the paper, and alpha. So beta is the coefficient by which things scale with respect to data. And more or less central limit theorem that we learn, law of large numbers that we learn in at an undergraduate level, tells us that this is no better than 0.5. There's usually a logarithmic correction. And so far we looked at the literature, including my own work, and we put the number 0.43 because this was sort of a representative of several test cases. So it turns out that by using some nominal errors, if you want to arrive at below 1% error in the field, not in the integral quantities, then you would need 2.7 million samples, which is very, very close to the number that you also arrived at, Neil. So this was not totally unscientific that these two things sort of coincide. So remember that we have this the scale at which, or the exponent at which, power law at which model size contributes, the data set size contributes to the error. So that's an important thing. The other thing is, of course, the scaling exponent with respect to model size. Now this is a fact that this is you need to grow the models a lot more to be able to ingest the data that you provide to them. So because there is a slower decay with respect to model size than with respect to data set size. So that's why you see some of the big numbers when it comes to model size in the paper. So these were the two key numbers that we fit in. We also added something like the number of copies that you want to see in transient training. What is the compression ratio that you are going to see? We put some reasonable numbers there. And the important thing was the flops. This is a similar question. This is a training flops per step. And this was finally, we put, I think, very, very aggressive numbers based on some use case that we had in the lab on some GH200s. We have assumed GB200s, and we assumed a very, very sort of aggressive scaling. In general, if someone is interested in figure 3, I think we have provided where we didn't provide this, but probably in the next revision we can provide that. But this is also a caveat. We were very aggressive, so these numbers could grow. And also the values of alpha and beta are not set in stone. Again, if you look at figures 3a, b, we sort of vary alpha, keeping beta fixed, vary beta, keeping alpha fixed. And then you can see how these different numbers change. And the important thing is, whatever you do asymptotically, at some point for large enough amounts of data, the model size has to be very big. So training the model will be very expensive, and it will overtake or dominate the cost of data generation. And this is sort of we have a theoretical demonstration of this, and we also see this empirically. But so this was sort of the logic. Maybe Johannes, you wanted to add something?
No, I mean this was perfect. And it's just one thing to underline. All these coefficients can change.
Yeah.
Change is not even the right word. They need to be determined scientifically, experimentally. But what we are quite certain is the slopes of these two curves. And that is, we were quite surprised that the data generation has a different slope than the model training. And the model training, at some point, the slope overtake the data generation slope. And this has big impacts in many ways. And this is one of the big findings, I would say.
Yes, so just to paraphrase, data generation scales linearly with data set size. Model training scales superlinearly. How superlinear depends on this alpha and beta, but it will always go superlinearly because the model is always going to be slower in scaling than the data. And then eventually you'll have a crossover point.
Yeah, that's kind of the real teaser, I guess, because you're right. Nobody, or publicly anyway, is doing these sort of huge data set generation. So it's kind of hard for us to put it out. But as soon as that does happen, it would be very interesting to compare because, as you say, if you take all you're doing is delaying it. So let's say you imagine the data generation's on a CPU, and all those numbers are 10 times higher.
Yeah.
It just means from our prediction that the crossover point will come later.
Yes.
But it will come at some point. And so it's almost then the question is, well, from a usefulness point of view, how big does the model need to be to give a low enough error and a broad enough generalization? And depending on that, it will seem to infer where the biggest cost and investment is, but also, and maybe this is a good segue into some of the open questions. One of the topics that I went into writing this paper thinking would be a bigger one, but I think in the end, the scaling laws more dominated the discussion. And I think we agreed that we just didn't have enough information to write on it, was some of the online training. That sense that the data generation cost is so big that you want, and the cost of storing the data is so high that you need some way of doing it online. And I still sort of get that feeling, but the timescales difference. We assume that the model training is super fast and generate the data takes ages. But at some crossover point, when the model training takes forever or very long time, and you sort of wonder where these are going to come in. And it is interesting that I should also caveat, the storage numbers assume very heavy compression.
Yes.
So we should put a sort of caveat out there that the storage may still be quite a large cost. And also the storage I'm picking here is, quite a cheap object based storage system. And this is not like a Lustre file system that you're dumping on. That would be like 7 times more expensive. So I don't know, what did you feel as the key opening, the open questions? Maybe comment on the online training. How much do you see that as being important, overblown?
I just add one thing to the storage. So there is this very interesting phenomenon that we're training surrogates, and surrogates always make errors, right? So usually in compression, if you do text or images or videos, you basically want to go for lossless compression. But if your surrogate or your model is making an error anyways, that means your compression can also have an error. This error just needs to be smaller than the error the surrogate is making, which opens a huge field of research. I shouldn't probably say that loud, but I think that there's a lot of potential in that. And the second point, which is super intriguing to me, is the data mixing. I don't think what we did in Aurora, that punching data together and just doing the mix is the way forward. I think that having a clever formulation of how you can leverage different fidelities in that sense, or different that you stay as cheap as possible in the data generation side, while being as performant as possible with the highest fidelity on the modeling side, is one of the key open research points to discuss, which is super, super hard, because that means you have to operate on scale. You have to really bring these communities together. You cannot do that in a machine learning lab without CFD expertise. You probably cannot do that with, but that's where the fun begins, I would say.
Yeah, and I don't know whether I'm allowed to say this aloud, but we discussed this quite a bit. We even had different versions of the write-up where we had different models on how we can sort of combine data and so on. We had different strategies. Maybe that should be a separate paper altogether at some point. But I agree with you, Johannes, that this is a super interesting question. And also this question of cross-learning that you raised, Neil, right?
Yeah.
So how much of information can be, in my day job as an academic, I'm very, very interested in that. How much of physics can be learned from other physical effects? Can you learn diffusion from fluid flows? With Poseidon, we showed that this can be done because somehow it is hidden inside. So these are the sort of scientific questions which will be hopefully answered in the year or two, right? But we cannot wait for things to. So the best way to generalize is to make your distribution so large that everything is more or less an in-distribution problem. We have seen that with language modeling, right? So I think putting these numbers out, telling people that, hey, look, this can be done, provided that there are these, and people can make their own choices. Maybe I don't scale my model at all, and I simply say that my model has 50 50 billion parameters come what may. And then at some level, as you generate more and more and more data, all that it does is that the model doesn't improve because it's dominated by your modeling error, right? So the model error, not the modeling error. So these are choices that people can make, and they will make pragmatic choices, but at least it gives a ballpark of what people should aim for. So I think that's what is very interesting outcome of this project.
And I think, at least from my perspective, that still feels like the unanswered question. We were hoping, or at least I was hoping, that we would have a little bit more of a definitive answer on this topic, which is, if I train the model with the RANDs with a certain level of error, and then I also give it some LES with a certain level of error, how can the ML model know that one was a RAND and one was a big? And we touched this a little bit in the paper, but this, we have, I feel, set the question right with the equation 9, but we haven't still fully answered how you would use and mix all those different inputs. That for me feels, we tried it, and I think we felt it was just, we didn't have enough data to fully answer that question. But that feels like you're right, because the point being is that you may not have the luxury of generating all this data from scratch. It may be pre-existing data where it has had a certain modeling error or a certain boundary conditions or a certain fidelity. And you need a way of the model knowing that, rather than saying, well, everything will be an LES and everything will be. That still feels like, a key thing which is not clear, right?
And my take is, so there's two opinions on that. My take is, and I think I agree here with Sid, that you had to get rid of categorical distributions, because categorical distributions is the arch enemy of generalization. On the other hand, people say, okay, it's basically a multi-task learning, because the model learns two different tasks and the weights share across these two tasks. I cannot comment because it needs experiments. It needs large-scale experiments. But I'm just convinced that categorical formalization is just very, very hard to, because you never get then out of this out of distribution problem.
Yeah, but the reason we did some of this scaling laws or example was, even if you could make the data generation half the cost, you would still at some point have the training to be the biggest, right? So there's no free lunch in that sense. If you do it all with RANDs, yes, compared to the estimate we had, maybe it's half the price of the data generation. But if you still believe that you need millions of samples, then you're just shifting it more to the model training. But then how do you fix the ultimate issue that the RAND's error, unless you come up, which is where the full circle is interesting and we didn't talk about too much in the paper. There is still a reason to come up with the ultimate RAND model. If you could use AI to come up with the ultimate RAND model, you would ultimately make the data generation cost quite a bit lower. But the reality of that happening, as you said, is a much harder problem, ironically. But there is some motivation for it. Maybe one of the other final topics that we should cover, maybe we should come back and have another discussion on this when we've had more feedback from the community, is the inductive bias one. I think we were quite deliberate in saying we'd already stretched ourselves with making hypotheses and making assumptions, that I think we didn't feel this was the right time to have too much of a dedicated opinions of including physics. We wanted this to be a little bit more of a like a data-driven, like how much data do you need? What's the scaling laws? It's still an open question, right? But it feels one where you would need quite a lot more paper space to get into this. I don't know what you both think.
Maybe
I let Sid answer, because I will burn if I answer here.
Okay, to put it as politely as possible, we don't know, right? This is a reality. Means, I think the belief that one way to put physics is just to know what the governing equations are and stick them into the loss function. We know that there are some difficulties in training this. The training is ill-conditioned. You have to precondition it somehow. There are some ways out there, but this is far from what we are already able to do with the data-driven approach. Far from it, right? With the data-driven approach, we are able to predict the weather now, which is a physics-based problem, and it's done in a data-driven approach. So I don't think the question of how to add physics has been answered yet, even in an academic setting, let alone in a large-scale setting, right? So you could argue that maybe we can put in conservation laws, symmetries. I think there are some comments about that also on the post. Yes, that could be. We could use that as data augmentation and so on. But I think it would still be a low ball. It's not going to change things dramatically, because maybe the physics has a lot of hidden symmetry or explicit symmetries, but the boundary conditions break it, right? And then, where do you go? And so and sticking the sort of a physics equation-based loss so far has not been able to be shown to scale at this limits, but maybe it's possible.
Yeah.
So I think the question of how to add physics into these models is a very interesting one. In my opinion, it has not been answered yet. And
and I think one of the points of this paper, which I was keen, and I think maybe sets it apart from some other recent papers talking about foundational models, is it is unashamedly a more industrial focus. Like, if you want to build a model that could predict a car or a plane or a data center using the architectures available today, how would you do that? And so that is why it doesn't focus on stuff that could be around. It is essentially saying there are architectures available today. How much compute and data would you need to throw at it to build the model? That is essentially the summary, isn't it? And what is undeniable is there will be future architectures and future ways of doing things that could incorporate it. But I think what we're setting out is if you've got enough, compute budget and data budget, it feels like this could be done, right? I mean, that's the sort of takeaway I'm getting from this paper, is that if you have a efficient enough data generation code and a scalable architecture, the only limitation is compute. And I think because of that, I would make a prediction that we will see people try and build these models, because those numbers are not so high that they are beyond, especially in the age of AI, stuff. So hopefully that formalizes a little bit, that at least from our numbers, this, and I say this, and maybe this is the final point, it'd be good to get your final. There was an early version of the paper where I wrote at the bottom of the, I think, abstract, something like, we conclude that this is an untractable problem, that you cannot actually build it. And and I had to completely change it, to basically the other way around, because I believe now it is a tractable problem. We don't know how accurate it'll be, right? So I think it can be done. What's your final thoughts?
Yeah, that's a beautiful ending, and not much to add. Just saying, it can be done, but not for all CFD. So not for all the cases you listed in Appendix C together, but for certain specified set of cases, either together or separately. It depends on where you're looking. But industry doesn't need a model which works for all CFD. Industry needs a model which works for the type of problems they're looking at. This does not only apply for CFD. This applies for all sort of other problems, semiconductors, crash testing, blah, 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 blah.
Yeah, being a sort of the more the scientist here, maybe I can say that, the scientist's dream is to have this large scale model. I think we are close. Maybe because our main assumption in terms of data generation, I think we have laid the case very well. In terms of model architecture, we have made the hypothesis very clear that your model has to scale in a certain manner with respect to data and with respect to model size, right? There are architectures out there which can do that. They can certainly do it in sort of specific domains, as Johannes rightly said. Whether they can do it cross-domain or not, this is essentially my research. I'm occupied with that question all the time. I think hopefully the answer is yes, but certainly in a sort of restricted setting that Johannes said, I think our numbers clearly show that this can certainly be done. But let's be optimistic and say that at least in some cross-domain settings we can still do it. Soon enough, rather than waiting for 5 years.
It's been a pleasure. We'll have to do this again. So thanks, guys.
Thanks a lot.
It was an absolutely pleasure not only writing this paper, but also having the podcast with you.
Yeah. Awesome. All right. Thanks.